What do you know about clouds?
Yeah. And again,
I need to think of
yeah,
that.
that's okay. Okay, welcome back for another exploration of liquids and gases. Again, I'm joined by Pasha. Say hi, Pasha.
Hello.
This time we're going to be talking about clouds. And Pasha, can you tell me what you already know about clouds?
The cloud is a big block of vapor with some liquid inside it.
Yeah, for sure. Okay, any particular type of vapor if we were thinking about like water clouds? Yeah, okay, so we've probably got some water. Now, our job today is going to try and create a cloud inside this bottle and also explain how that process is happening. So at the moment, this is just an ordinary bottle. I mean, naively, I might say there's nothing inside it, but of course, you being a chemical engineer would say there is or obviously something in there already. What's in there?
Air.
Absolutely. So we've got some air in there. And you said to me that one of the ingredients that we need to make a cloud was to add some
Air.
and
Water.
water. Absolutely. So we're going to add a little bit of water. And you mentioned this word vapor before. So in order to get that water vapor, what we'll do is we'll shake this bottle. So I have a little bit of liquid water at the bottom. This is actually still warm from our previous experiment, but it doesn't have to be. Now I have some water vapor in here along with my liquid water underneath. And I would like to be able to create this cloud. And you mentioned that we've got these droplets of liquid that make up that cloud. What would we do to this water vapor in order to turn that back into droplets of liquid?
We would need to condense it.
Yeah, absolutely. And can you think of any ways that we could condense this? What would need to happen to this vapor
To cool it down.
to cool it down? Absolutely. So whether or not you start with warm water or with room temperature water, it's absolutely possible to do this demonstration like this. Now, to link in with our idea from before about boiling and evaporation, I'm going to emphasize to you that as I squeeze this bottle, I will actually be doing mechanical work on the gas here. I'm actually heating the gas. So I'm going to squeeze this gas. Okay, and then as I pause for a second, of course, that gas has the opportunity to lose some of that heat to the surroundings. So right now, even though I'm squeezing this gas, it's probably about the same temperature as it was just before I squeezed it. Does that make sense?
Yeah.
Yeah. Now, when I let it go, now the gas is doing work on the surroundings. It's pushing apart the bottle again. And so compared to before I let go, is the gas a little bit warmer or cooler?
Cooler.
Absolutely. So through this process, we can try and cool our gas down. I'll squeeze, I wait, it loses a little bit of that excess heat to the surroundings. And then when I relax my hands, then it will start to cool down. And I can repeat this process. But it doesn't look as if we're making a cloud. So we need a bit of an extra ingredient. And we think about what that ingredient might be and how that can take place. So let's talk about why we didn't immediately see a cloud being produced here. In order for us to produce a liquid droplet, we need, when two of our vapor particles are going to collide, they need to be able to collide with low enough energy that they're going to be able to stick under their mutual attractive forces. The problem that we have, though, is that assuming maybe two of these just so happen to stick, they're surrounded by lots of other particles that could bump into them and break apart that building droplet. Each particle only has one other nearest neighbor to which it is attracted. As a droplet gets bigger and the curvature at its surface decreases, though, it's possible to nestle it in among more and more particles with which it can form attractive forces. The chances of it being lost to the vapor again start to reduce. Now, I'm being very deliberate here to emphasize that in this bottle right now, we have two competing processes, evaporation and condensation. Many students, indeed research shows even teachers think this, tend to think that once something has evaporated, that process in a sealed bottle essentially is complete. The numbers of particles in the gas remain constant. They don't think in terms of equilibrium. So Pasha and I, we're going to play with the system now by adding some kind of framework on which we could build some droplets And then those droplets don't have to start from nothing. They might actually be able to grow much more successfully. So we're back into chemistry mode, Pasha. What I'd like you to do is light this splint, okay, get it burning for a couple of centimeters, and then once we've got a couple of centimeters of flame on it, I just want you to extinguish it so that it's smoking, and then we're going to wave a little bit of smoke into the bottle there. Okay, so we just wafted around a few smoke particles, and that's enough, yep. Obviously, we have a little bit of smoke in there, but would you agree that it would be unfair of this to call this a cloud, right?
Yeah.
We're going to do the same process. In fact, you can do this now. I would just sort of hold it here so we're not right in front of the microphone a few times and see what we can see happening. Okay, if you pause there, what will you notice?
The cloud disappears when I press and reappears when I let go.
Yeah, absolutely. So, and if we repeat this process a few times, we've definitely got something in here now. This is more than we just sort of placed in. And in fact, we can actually see that is not the smoke that you put in. Would you agree?
Yeah.
Yeah, we just made a cloud. Now, what we've demonstrated there is good enough for lower school students, but if we really want to get a solid idea about what's happening, maybe this is where we would sketch a particle diagram, and we'll figure out whether or not we want to tell anybody where you just graduated with your chemical engineering degree. It's okay to make a mistake here. We're all human. So, I've got a couple of diagrams to show our bottle, which is sort of before we squeeze it, and then a bottle when we squeezed it. And all I'm asking you to do here is sort of think about particles in the vapor, particles in the liquid. How would you show the difference between when we had the vapor to begin with and the liquid, and then you squeezed it afterwards? Gas. Gas. Think about the numbers of particles you're drawing. Think about where they are. Okay, so a few minutes later, Pash has drawn for us our diagram. Do you want to just talk us through? We've got some green dots in both situations. What's being shown?
Before squeezing, we have water particles inside the water being more spread out. And after the bottle is squeezed, the particles are being pushed closer to each other, making them, well, closer to each other.
And we were talking before about like the numbers. If you were to count these particles on the left and the right, would there be more on one side, more on the other, or what?
I think that would be the same.
Yeah. Again, this is actually like what most people, especially like even student chemistry teachers, and I would dare say quite a lot of chemistry teachers who are more advanced, might naively sort of move towards, because it feels as if like this is kind of like an ideal gas law type scenario that we would imagine. We're squeezing our bottle, and therefore we've got these particles that are pushing back against us. But what we're forgetting is, of course, that we have some liquid down here at the bottom. There's also an equilibrium taking place. So many student teachers, just like yourself, you are not alone, I promise you this. Many teachers also will have made this kind of error in their model where they weren't necessarily recognizing that actually this is a two-way street. A lot of people begin to have this idea that I've got my gas in here, and once I have those particles in the gaseous state, they kind of stay there. But it's a dynamic process that's taking place here. So what will actually happen is that as long as we have the system at the same temperature, the vapor pressure actually is going to be the same in both of those situations. As I squeeze here, all that will happen is that I will force or encourage more condensation to take place. And so actually the overall vapor pressure of the water in here is going to be reduced. The overall pressure will be higher. You know, you can feel it pushing back against you, but that is the pressure of what's the other thing that's in here? Air that's also in there. And it's totally okay. And you can kind of see how you can explore this demonstration with quite young students and just get them to focus on evaporation and condensation. But even older students and some teachers can also benefit from talking this out and giving it a go. Hi, this is Declan from the future doing the video edit right now. And, you know, sometimes it's really tricky to to keep everything in your brain when you're trying to explain something on video while still allowing the possibility for something to veer wildly off script. And I wanted to redraw Pasha's diagram for you to help it show up on the screen, and I noticed something that escaped me in the moment. I was expecting Pasha's instinct for conservation of mass and the ideal gas law to kick in. He must have had a very good chemistry teacher. And so when he gave me the expected wrong answer, that the numbers of particles in the water vapor would be the same in both scenarios, I just moved on because that's kind of where I expected the video to go. But looking back at this now, I feel like even if that wasn't what he said,
I think that would be the same.
it almost looks as if he might have begun to draw, let's call them nano droplets forming. And I wonder now, had I taken the conversation in a different direction, I might have got him to intuit that he was beginning to show that actually the number of particles in the water vapor were reducing as droplets of mist were forming. If they ever watch this, I think his lecturers can be really proud of him. I know his old chemistry teacher is. So Pasha, I want to thank you so much for joining me for these videos. It's been really helpful to see how you think, and I hope the audience will have benefited as well. I hope you give these experiments a try and that they help you strengthen your own mental models for what's going on. Say goodbye.
Thank you.
Goodbye.